Okay, so this is Math 146, Section 7.3, the final section of the course. We are going to be talking about the binomial theorem. I'm going to be completely honest, this is probably one of the least practical when it comes to its use, but at the same time, it is probably one of the most fascinating sections. And there are some practical uses, don't get me wrong, but there's probably other ways that we're going to be able to come up with, or the idea of having to use this for what it is probably just isn't really going to be something that's very common. But that being said, again, I think this is one of the most fascinating, and I hope that you find it pretty interesting as well. So the binomial theorem, the general idea is if you're given some kind of a binomial and you want to expand the binomial, for example, if all we had was x plus a, technically that's to the first power. Well, there's nothing to expand. That's just x plus a. If we took x plus a and raise that to the second power, well, then we know we would have to expand that. FOIL would probably be the easiest method to do here, in which case you would get x squared plus 2x times a plus a squared. Now, one that gets a little bit more complicated is if you had x plus a cubed, and I can tell you that that would be x cubed plus 3x squared a plus 3x a squared plus a cubed. And I know this because I know the binomial theorem, or I know something similar to the binomial theorem that's going to help me to do that. We could go ahead and expand out x plus a to the fourth, and we could keep going if you know some basic things. So what I'm going to tell you is that what this comes from is a notation which looks like this. And you will see this heavily used in probability. But what this means, it's actually red. It's red. That's why it's in red. No pun intended. Actually, pun was very much intended there. It's red. N taken J at a time. So what that's telling me is I've got N things, and I'm going to take those J things at a time. Again, this is something which is heavily used in probability. Um, know that J has to be less than or equal to N at all times, and at all times these are positive values because the way these are defined are through factorial. So these have to also be whole numbers. So this is the definition of how it works. So N things taken J at a time is defined to be N factorial divided by J factorial multiplied in the denominator by the quantity of N minus J factorial. Okay, so in other words, the general idea is, let's do one that's very, very general. If I have N things, and I want to take all N things at one time, well, there's really only one way you can do that. So if I have 5 things and I want to take all 5 things all at the same time, that's going to ultimately be 1. And we can show this by the definition, because according to the definition, it is n factorial divided by n factorial multiplied by n minus n factorial. Of course, the n factorial on the top and the bottom are going to cancel out, leaving you with a 1 over, and then the n minus n is going to give you 0 factorial, and by definition, 0 factorial is 1. So ultimately, that gives us 1. If I wanted to take n things and I wanted to take them one at a time, well, you would expect, like, again, let's just say it's a 5 on top. If I take 5 things or have 5 things and I want to take them one at a time, well, there's going to be five things that I'm going to take out. So it should end up ultimately being 5. Well, in this case, since I have n things and I want to take one out at a time, so I'm going to take them one at a time, then it should simplify to n. And let's see that that happens. So that would be n factorial divided by 1 factorial times n minus 1 factorial. So let's simplify. Well, 1 factorial is just 1, so that basically becomes a 1 in the denominator. But then on the numerator, I've got n factorial, which by definition is n times n minus 1 times n minus 2 all the way down. But that is the same as n times n minus 1 factorial divided by n minus 1 factorial, which leaves you with just n. All right, so that's the way this works in general. Let's put some numbers to it and so we can actually see how this works. And again, some of it should be slightly more intuitive. Some of it will not be. So if I want to take, or excuse me, if I want to have 3 things taken one at a time, you would expect that this answer should be 3, because if I've got 3 things, I take one out at a time, 1, 2, 3, I've got an answer of 3 because I've taken 3 things out one at a time. So it should be 3 factorial divided by 1 factorial multiplied by 3 minus 1 factorial. Simplifying, you get 3 factorial divided by, again, 1 factorial is 1, divided by 2 factorial. And we can actually write all the terms out on this one, but that would be 3 times 2 times 1 divided by 2 times 1. And again, this 2 times 1 on top is the same as 2 factorial. And then, of course, that's 2 factorial down there. So you end up with just 3 because the 2 times 1 on the top and the bottom cancel out. One that maybe not as intuitive would be something like 4 things taken 2 at a time. Well, I mean, it really should be kind of intuitive. But there's different ways you can do this one, because of the fact that you can take 4 things 2 at a time in several different methods. So if you were to write out 1, 2, 3, 4 things, I could take those 2 things first and then those 2 things second. No problem there. That's 2 possibilities right there, right? But I could also take this one and this one first, followed by the middle 2. So that's another 2 possibilities. Or I could take, let's do a different color. I could take the first and the third one first, and then I could take the second and the fourth one later. Well, that's another 2 possibilities. So there's multiple different ways that this could work. So let's find out exactly how many there are. I think I actually covered them all. There should be 6 if I'm not mistaken. So we'll take 4 factorial, divide that by 2 factorial, and then we're going to multiply the denominator by 4 minus 2 factorial. So we have 4 factorial divided by 2 factorial times 2 factorial. And 4 factorial is defined to be 4 times 3, and then technically times 2 factorial. Over 2 factorial, 2 factorial. One of those 2 factorials is going to go away. So really what you have is 4 times 3 divided by 2. 12 divided by 2 is 6. So we really did have 6 different ways this would work. Let's try 8 things taken 7 at a time. Okay. There really shouldn't be a ton of possibilities, but there will be a number of them. So we'll have 8 factorial divided by 7 factorial times 8 minus 7 factorial. So we're going to have 8 factorial divided by 7 factorial, and then 8 minus 7, of course, is 1, so that would give me a 1 factorial, which itself is 1. So really what I have is 8 factorial divided by 7 factorial, but of course 8 factorial is 8 times 7 factorial, so those are going to go away, and that leaves us with 8. So there's 8 different ways that you could do this, taking 7 at a time. And again, that should make sense if you think about the fact that you could take the first 7 of things. Okay, that's great. I could take the first and then skip the second one and then have things 3 through 8. And then I could take the first one and I could skip one, skip 2. So I could take the first 2, skip the third, whatever. There's a whole bunch of different ways to do it, but there's 8 total ways you could do it. There is actually a way to do this in your calculator for bigger ones, because if I asked you to do something like 65 things taken 15 ways, I don't expect that one to be something you would do by hand. I mean, you could certainly write out what it would look like. It would be 65 factorial divided by 15 factorial times 65 minus 15 factorial. And that would simplify down, before we do any numerical things, to this. And that is not something right there that I would expect you to do by hand. Your calculator can compute that, but that's actually a really, really large number. It's some kind of a decimal times 10 to the 14th power or something like that. But again, that would be something you could use a calculator for. Not something I am going to require for anything. Okay, so why are we even bothering with all this? What does all this stuff have to do with what I was saying about expanding a binomial? Well, there is this thing that I learned a long time ago, and I'm sure that I learned it as part of the binomial theorem, but I have come to just know this as Pascal's triangle. And Pascal's triangle basically starts with a 1 at the top, and then it's got a 1 on the outside, and all the way down the outsides of the triangle are 1s. But the middle part, so this part right here, in the middle is going to be the sum of those two numbers. Well, 1 plus 1, of course, is 2. And then if I go to the next level, 1's on the outside, and then I'm going to take the sum of those and get 3. But then I also have the sum of those two and get 3. And then if I do it one more time, and this goes on infinitely, but if I do it one more time, now the sum of those two is 4, the sum of those is 6, the sum of those is 4. What you have is you have the coefficients for an x plus y, or an x plus a raised to some power. So how does that work? Well, this would be x plus a, technically to the 0 power. 0 power would make that 1. Well, that's exactly what we have right there. It's just a 1. This one would be x plus a to the 1st power. Well, the coefficients of the x and the a happen to both be 1, which is what these values right there give us. Then we have x plus a to the 2nd power. Well, if you remember when we expanded that, it was x squared, so that's 1x squared, and then it was plus 2ax, there's your 2, and then it was plus 1a squared, and there's your 1. It's the coefficients that you're going to get when you expand these binomials. And then the last one, again, would be an x plus a cubed. It was a 1, 3, 3, 1 pattern. So this is what I use to figure out, and that's actually what I was thinking of when I had to expand the binomial to the 3rd power. I use Pascal's triangle. To me, it's easier than doing what we're getting ready to do. However, what we're getting ready to do is also going to work for anything. So if you had to do this to the 10th power, you may not want to write out the triangle all the way to the 10th. You can, it's perfectly fine, but you don't have to, if you understand how the Pascal's triangle and the binomial theorem are going to work. So the thing that we did with the parentheses is what is going to give us what's called the binomial coefficient. And in general, this is going to be your general form for your binomial theorem. If we have x plus a raised to the nth power, what that's going to be is it's going to be n taken 0 ways, x to the n power. Technically, and I'm going to write this down, that would also be times a to the 0 power. But of course, that's 1, which is why we typically don't write it. The next one would be n taken one way, which would then be a to the first power x to the n minus 1 power. And what you need to understand is that the exponents of the a and the x always have to add up to n, whatever the n is. Okay, so the next one, you've probably already guessed this, would be n taken two ways. Then it would be a squared x to the n minus 2. And again, if you were to take and add those exponents up, they still add up to n. This is going to happen all the way until you get to the very last term, which would be n taken n ways. In this case, your x is now going to be all the way down to the 0 power, which makes that a 1, and then a will be raised to the nth power. Okay, and this works for any expansion of any binomial. I wish it worked for the trinomials and everything else, but it doesn't. It's a binomial theorem. So if we wanted to, and we're going to kind of ignore the Pascal's triangle, although I do want to actually label that because that's what I said it was called. Pascal's triangle, named for Blaise or Blase Pascal. I don't actually know how you say his name. I think it's French. Blaise Pascal. Somebody might know better than me on that one. He's the one that kind of came up with the idea of this. All right, so if we want to expand, let's just do an example here. We want to expand x plus 2 to the 5th power. X plus 2 to the 5th power. So x plus 2 to the 5th power would be 5 taken 0 ways. So you always start off with the nth power and then taken 0 ways. So that would be x to the 5th, because that's your first term over here. We start off with the x. So x to the 5th, technically it's 2 to the 0 power, which I will write. Okay, it's not always written that way, but I will write that, because when it becomes something other than a constant, we're going to need to write that down. Plus, the coefficient will be 5 taken one way, reduce the x power by 1, add 1 to the 2 power, plus 5 taken two ways, reduce the x power by 1, increase the 2 power. And again, notice how all the exponents still add up to 5 for each term. Plus 5 taken three ways, reduce the x power by 1, increase the 2 power. Almost done. 5 taken four ways, x to the 1st, 2 to the 4th, last one. 5 taken 5 ways, x to the 0, 2 to the 5th. I apologize, my numbers as I start to write further and further to the right hand side of this page are getting worse and worse. Try and correct those so it looks nice. There we go. So let's go ahead and write this out. 5 taken 0 ways, and again, we've kind of already talked about what that would be. It's a nice one to know. If you take an n value and take it 0 ways, there's only one way that can happen. So that is literally 1. And then x to the 5th is x to the 5th. 2 to the 0 is 1. 5 things taken one at a time means that there's only 5 ways that can happen. So that would be a 5. X to the 4th times 2. Okay, 5 things taken 2 at a time. I'm not going to walk through plugging that into the formula for you, but that gives you 10. And you could figure that out. X cubed times 2 to the 2nd power, which is 4. 5 things taken 3 at a time also happens to be 10. Believe it or not, it works out to be the same. X squared, and then 2 to the 3rd is 8. 5 things taken 4 at a time is actually going to be 5. There are 5 different ways that can happen. X, and then 2 to the 4th is 16. And then 5 things taken 5 at a time, there's only one way that can happen. X to the 0 power is 1. times 2 to the 5th is 32. So now we can just simplify. So what we have is x to the 5th plus 10x to the 4th plus 40x cubed plus 80x squared plus 80x plus 32. And we have expanded x plus 2 to the 5th power, as well as simplifying along the way. Now what I want to show you, going back to Pascal's triangle, here's your coefficient 1, 5, 10, 10, 5, 1. Okay, that's what you get from doing the binomial theorem, the little parentheses things. We didn't do it up here, but let's finish this one off, because technically this next one would have been the 5th power. The 1's on the outside. Adding these terms right here, you get 5. Adding 4 and 6, we get 10. Adding 6 and 4, we get 10. Adding 4 and 1, we get 5. It's exactly the same coefficients. The only part that's different here is because you have that extra 2 as part of your binomial that's going to give you extra values there. If it had just been x plus y, it would have actually been even easier because it would have been variables, no extra numbers to deal with. All right. So again, this is not a difficult thing to do. It's a little tedious maybe. The higher powers you go, the harder it is, the longer it takes to go. Now let's say we're going to add something in there where we've got, first of all, we've got a coefficient in front of maybe the variable, and you can have coefficients in front of multiple variables if you've got x's and y's in your binomial. But like we have 2y minus 3 to the 4th power. So if we want to expand that, again, the fact that there is a negative 3 in there is part of it, so that's going to make a difference. So that would be, again, we're starting with the 4th power, so that would be 4 things, just taken 0 at a time. The first term is 2y, which will be raised to the 4th. The next term is negative 3, which is raised to the 0. Okay, and then it would be 4 things taken 1 at a time. 2y, the entire 2y gets raised to the 3rd power, and then negative 3 to the 1st. 4 things taken 2 at a time. 2y squared, negative 3 squared. 4 things taken 3 at a time. 2y to the 1st, negative 3 cubed, and then 4 things taken 4 at a time. 2y to the 0, negative 3 to the 4th. I'm not going to expand the entire thing out here for you, but what I do want to point out is this. Because of the fact that we had that negative, that minus 3 in there, when I get to this negative 3 to the 1st, that's going to create a negative value. So it's basically going to make a minus sign here. This negative 3 is going to be squared, so that's going to keep that as a positive. And then this negative 3 will be cubed, which will make that a negative. And then the last negative 3, of course, is to the 4th, which will make that a positive. So your signs are going to switch. And technically, the first one is also positive. Your signs are going to alternate here because of the way this works. So just keep in mind that when you have a minus sign as part of your binomial, you will get alternating signs for your terms. But otherwise, the expansion is done exactly the same way. Again, I'm not going to simplify that. You can feel free to go ahead and do that. Where this might be slightly more useful is going to be, let's just say they want us to find one specific term of the expansion. So we don't need to do necessarily every single term of this whole thing. And obviously, they could ask you to find the term. They could ask you to find the coefficient. However, if you find the whole term, then you're going to have the coefficient as well. Let's say that we want to take something like x plus 2 to the 9th power, and we want to simply find what the sixth term is. So that's all we're looking for, is what is the sixth term? Well, you could certainly expand this thing out all the way if you really wanted to, till you figure out what the sixth term is, or you could just kind of figure out what term is it that's going to be required for me to get to the sixth term. The hard part is that you have to remember that you start off with 9 taken 0 at a time. So that's technically your first term. So again, remember something like 9 taken 0 at a time, x to the 9th, 2 to the 0 power. That would be your first term. So if I want to find the sixth term, I have to think that 0 is my first term. So 1 is my second term, 2 is my third term, 3 is my fourth term, 4 is my fifth term. So 5 would be my sixth term. So the one I'm looking for is the one where it's 9, whoops, not 9 divided by 5, 9 taken 5 at a time. Well, then you have to realize that it's going to be x to the fourth power, 2 to the fifth power, because you'd be reducing all the way down till you get to this point. So now we could actually figure out what that sixth term is. And that would be 9 taken 5 at a time, which is going to be 9 factorial divided by 5 factorial. 9 minus 5 is 4 factorial. Oops, and that equals x to the fourth. And then 2 to the fifth power is 32. So now we can actually simplify. Let's see, 9 factorial is the same thing as 9 times 8 times 7 times 6 times 5 factorial. So that's going to get rid of the 5 factorial in the denominator. And then 4 factorial is 4 times 3 times 2 times 1, x to the fourth, times 32. Now let's see what we can do to make this a little bit easier. I'm not saying these numbers aren't going to still be big. I think they will. But let's see here. I've got, I've got a 4 and a 2 in the denominator, which multiplies to 8. I can use that to cancel out that 8 right there. So those are gone. I've got a 3 in the denominator, which is going to be able to make that become a 3. So now I'm down to 7 times 6 times 3 times 32. Okay, those numbers are still kind of big. And if you don't want to work those out by hand, that's understandable. But you should get 4,032, and then it's times x to the fourth power. So that would be the sixth term. And if all they were asking you for was the coefficient, it would be 4,032. So that would be what you'd be looking for there. All right, so how can I use this to do some other stuff? Well, it's going to go all the way back to Pascal's triangle up here. Oops, too far. If I wanted to expand out something cubed, again, I kind of know how to do that because of Pascal's triangle, but you would basically be using that one right there. And if I wanted to use this, we're going to go all the way back to the kind of the beginning of the course when we did the difference quotient. Let's say that I wanted to do the difference quotient for, and we'll just do the one that we've used, x plus 2 cubed. Okay, we want to figure out the difference quotient of that. Well, if you remember, and this is going to go way back, the difference quotient was f of x plus h minus f of x, all divided by h. And actually, we're not going to do the difference quotient for that one. I apologize. We're going to do the difference quotient for x cubed. Excuse me. So you can see how this will be helpful, because if I want to do f of x plus h, f of x plus h, well, that's going to be x plus h cubed. Well, we need to expand that in order to do the difference quotient. So x plus h cubed. Now we already know this. The coefficient of the first part is 1 because it's a 1, 3, 3, 1 coefficient. Again, you could use the whole binomial theorem if you want to, I find it easier just to use the 1, 3, 3, 1, especially when there's 1s as coefficients. So that's going to be 1x cubed h to the 0. I'm not writing the h to the 0. Plus 3, and now reduce the x by 1, x squared, h to the first. Again, the exponents have to add up to 3. Plus 3 is the next coefficient. Reduce the exponent, increase the exponent. And then the last one is a coefficient of 1. Reduce the x to 0. 0 exponent, excuse me, and the h becomes h cubed. So I've gone ahead and expanded out x plus h cubed without having to basically FOIL x plus h times x plus h and then multiply another x plus h using whatever method you might choose for that. And then this becomes pretty quick and easy to deal with. So the difference quotient would be x cubed plus 3x squared h plus 3xh squared plus h cubed minus f of x, which was x cubed, all divided by h. And what we should see here is that these x cubes go away because I got an x cubed minus x cubed. So now we are left with 3x squared h plus 3xh squared plus h cubed, all divided by h. Oops, left an h off of there. Otherwise, this wouldn't have worked. So now we can divide the h out of everything, and we are left with 3x squared plus 3xh plus h squared. And that would be the difference quotient for x cubed. And that's why, that's one of the practical reasons you could use this. If you had to do it for x to the fourth, again, you could very easily plug in x plus h to the fourth, expand it out, and then work it out that way using this binomial theorem. All right, that is it. That is the last lesson for Math 146. Hopefully that is everything you need to be successful.